Good morning, everyone. Welcome to the class. Um, I'm going to talk about the transmission line structures and basic properties today. At the second part of the class, I'm going to talk about time domain analysis concepts, and also I would like to talk about the underlying physics on the transmission line. Let's think about a case. What happens if we want to send a signal from us to the moon? Let's assume that we are connecting from us to moon using a wire. Then the length of wire will be 380,000 kilometers. It is going to be a long distance from us to moon. And then in circuit theory, it's becoming an inductor. Because it is wire, the magnetic field will be generated around the wire if you are sending a current or voltage along this wire. Then usually 1 millimeter wire produce a nanohenry. And by considering this whole distance, I think the total inductance might be 380 Henry. If we assume that source impedance is 50 ohm, time delay RL divided R time delay with respect to circuit theory is going to be 7.6 seconds. So we cannot send high-speed digital signal from us to moon by using a wire. That is, if we scale it down, even though your semiconductor device size is less than a centimeter, you cannot send digital signal by using a wire because it has too much inductance and it has too much time delay. Another problem related to this simple issue is that we're gonna have, we should have return path because in circuit theory, we wanna conserve the charge. That means current to the moon should come back to the earth to make a loop. That is the key of current loop theory. Then because you are using just single wire, we do not have a return current. So return current will go through this parasitic capacitance. So the parasitic capacitance between Earth and Moon may be very, very small number. So it is very hard to make on low impedance return current path. So because of that, if frequency is becoming higher and higher, this wire is becoming an antenna. So then, because of the distance, we have to apply the far field theory. That means the received electromagnetic field at the moon will be extremely small. Anyway, in circuit theory, if we have inductor and resistance, we're gonna have resonances. Because of that resonance, the impedance will be very high. So we are not able to send very high-speed digital signals from us to moon using the wire. If we scale it down, this problem to semiconductor circuit, still this kind of story will occur because even though distance from a circuit to circuit is very short, like less than a millimeter, still we cannot send high-speed digital signal using a wire because we have to provide the return current path, and also we have to worry about resonances. In some cases in the circuit, even though wire length is less than a millimeter, still it's gonna be an antenna. So In high-speed distal circuit, we cannot use this wire for transmitting the distal data from Earth to Moon. It is becoming data on antenna. When you are at high frequency, it becomes an antenna, and the signal propagation from Earth to Moon will have speed of light. And if you, because of the long distance from Earth to Moon, even though you are sending high power electromagnetic waves, the amount of received power at the moon will be extremely small, like a nanowatt or picowatt. So usually we need a large antenna size or array antenna, or sometimes we need an amplifier. And more important thing is that this inductance and this capacitance, the impedance of this loop will be depending on frequencies. And also the antenna properties of this wire is very depending on frequencies. So that means that in the distal transmissions, as I mentioned many times, the spectrum of distal signal start from DC to very high frequencies, many harmonics of clock frequencies. So the property of this data transmission from Earth to Moon should be frequency independent. But however, in the conventional circuit using a wire or antenna, it is very frequency dependent. So that's why we cannot use this circuit or antenna to send high frequency distal signals. That's why we have to use a transmission line structure, and that is the focus of our class today. This is summary of to talk about the limitations of circuit theory. The first, our distal signal has very high frequency component, and it has broadband spectrum with very higher harmonics. And also conventional circuit has large parasitic such as inductance and capacitance. So also conventional electrical models such as resistance, capacitance, inductance, and transistor model is not accurate at high frequencies because of parasitics. And also circuit theory does not consider phase delays with the length of interconnection. Also in time domain, they are not considering the propagation delay. So those are the limitations of circuit theory. And also in addition to that, in our class, we're gonna think about return current path. Many of the return current path is coming from parasitic current path. We should be able to visualize those paths. In addition to that, because of the wave property of high-speed distal signals, we have to think about reflections and termination impedance. So in order to control these reflections, we have to control the impedance of line, and also we have to control the phase velocity of your interconnection. I think these topics will be covered today and Wednesday classes. Now, I'd like to summarize the requirement of transmission line. Transmission line will give us constant impedance and constant phase velocity overall frequency range. Please remember that this is the basic requirement of transmission line. We usually have three different types of transmission line. This is the two-wire system. First one is two-wire system. Second one is the coaxial cable. And the most common interconnection structures at circuit and PCB and package level is the planar transmission line structures. In this type, this transmission line structure is being called as microstrip line structures. It has ground plane and it has a signal line. First requirement of the transmission line structure is that we have to have at least two or more metals. In these three cases, you see that we have two metal system, signal line and ground line, and signal line at the center of coaxial cable, and the ground return current path is at the shield. Here we have signal line on the top layer and ground line is on the bottom layer. In those cases, we have a two metal system. By using this two-metal system, we can confine electromagnetic field between the two lines, and we can confine electromagnetic field between the two lines. If the cross-sectional dimension is much smaller than wavelength, we can neglect the phase delay or propagation effect at the cross-sectional structures. Then we can define voltage and current at the cross-section, and this voltage and current will propagate as a speed of light along this line. So this is actually one-dimensional electromagnetic wave path. Transmission electromagnetic wave will propagate along this line, and along this line. So that means that this is one-dimensional waveguide. In order to be able to define voltage and current, it should have very small cross-sectional dimensions. Length should be long, but cross-sectional should be as small as possible. That is why this structure is very suitable for transmission line structure at PCBs and on-chip interconnections. And because of these small dimensions, we can define voltage and current at cross-section. Along this line, we have to consider wave propagation effect, but at the cross-sectional dimensions, we can define voltage and current at this cross-section. And then electric field and magnetic field will be confined between the metals. The effect of this metal is to confine voltage and the electric field and magnetic field between the two metals. Then, because of the Maxwell equations and electromagnetic field theories, electric field will be directed from top metal to bottom metal, and magnetic field will be perpendicular and will be lateral directions that will be tangential to the surface of the metal. That is the basic static field theory, because we assume that this cross-section is very small. And at this moment, and next week, or a week after next week, we're gonna think about the high frequency loss of the metals. But at this moment, we assume that it is lossless metal like superconductors. Also, we are going to assume this dielectric material that is filling the insulator between the two metals. We're gonna assume lossless dielectric materials. I think these 7 conditions, as certain conditions, these 7 conditions are requirement to meet the transmission line. In other words, I would say that if you are going to send high-speed digital signals, including clock signals or high-speed I/O signal between GPU and memory, your interconnection structures has to meet this requirement. But below 1 gigahertz or 1 gigabps, most of interconnections at the chip and PCB levels meet this requirement. So you can design this interconnection structures easily. But if the frequency is becoming over 10 gigahertz or over 10 gigabps, many of these assumptions will not be valid. So you have to carefully design your interconnections, or sometimes you have to design your I/O circuit to compensate this effect. For example, in number 6, we are assuming lossless material and lossless dielectric materials, but at high frequencies like over 10 gigabps, it is not true anymore. So you have to design I/O circuit or receiver circuit to compensate these high frequency losses. And those are usually being called as equalizer circuit design. So in the future, when you are designing your interconnection systems, you have to design your I/O circuits and interconnections all together. Number 5 requirement is that this dielectric material has to be the homogeneous structures. That means the most ideal structures for this transmission line should be, you have to have a single material who has the same dielectric constant. But in these microstreamline structures, you can see that some of field will be exposed to the air, and most of the electromagnetic field will be confined between the two metals, which will have identical homogeneous materials. But in many cases, your electromagnetic field will be exposed to air. Then in this case, it is not homogeneous. It is inhomogeneous dielectric environment, then high frequencies, speed of your propagation and impedance will be frequency dependent. So number 5, number 6, and number 7 will be very important to send very, very high speed digital signal from or source to receiver. And number 4 will be very important requirement to reduce EMI, EMC, and crosstalk issues. So, but anyway, if your structure has ability to meet all these 7 requirements, we can call it as a transmission line. And then we will have constant, very important property, constant impedance over a broad frequency range from DC to very high frequencies. At this moment, I would say our on-chip interconnections and PCB level interconnections should meet this requirement over up to maybe 10 gigahertz. But in the near future, we will be pressured to meet this requirement over 100 gigahertz. Then in over 100 gigahertz, number 4, number 5, number 6, number 7 will be very difficult to meet. And second property of transmission line will be the constant propagation velocity of overall very broad frequencies. And also these are very ideal graphical 3 structures: 2-wire transmission line, coaxial cable, and microstream line. But that has to be the structure should be a structure where we can easily implement in the chip, PCB, and packages. Now, let's talk a little bit about the difference between the lumped circuit theory and transmission line theories. In using the simple equation, I would say in the circuit theory, voltage is represented by amplitude of voltage multiplied by sine omega t minus phi. That means your voltage will be depending on frequency of your signal and your time to measure the voltage. Also depending on your position of measurement before a device or after a device, or whether you have inductor or capacitor or resistor, you may have different phase. So these are the basic assumptions of the lumped circuit theory. This will be very useful when your circuit size or your circuit dimensions are very, very small compared to wavelength of your signal. So let's assume that if your circuit size is less than a micron or 10 micron, this might be applicable. But if your circuit has millimeter or more sizes, this circuit theory may not be applicable anymore. In circuit theory, but however, in transmission line theory, we have one more parameters here, minus beta g. That means depending on your position, your phase of your signal will be different. So this beta will be responsible for speed of your electromagnetic signals. And so we have to consider that. Because of your voltage is depending on the frequencies and time. At the same time, your phase of your signal is depending on the position. Because of Wt minus beta g, this will propagate as a speed of light. Because of constant of this phase, Wt minus beta g, if you want to have same phase, your phase will depending on both time and the position. Because of this property, you're gonna have propagation properties. Also, sometimes you may have some lumped device along your transmission line, you're gonna have different phase. So major difference between the circuit theory and transmission line is the presence of beta G, position dependence of your phase. So your voltage and current will be just in the circuit theory is just time varying. And in your circuit theory in undergraduate class, a lot of your you spend your time to find a solution of voltage and current, assuming this time dependent. So you solve it using differential equations, or you solve it in the frequency domain using this transformation or S parameters. But in transmission line, your voltage and current are traveling voltage with not staying and is traveling. In the circuit theory, you describe your circuit element using resistance, inductance, and capacitance. We can think about why we only have 3 elements, because that is the derivative property of Maxwell equation. It is representing by second order derivatives of the circuit behavior. So R, L, C are enough elements to describe all the voltage and circuit behaviors. Actually, it is coming from Maxwell equations. If we do not have A, B, C, D, or something like that, we only have 3 elements and transistor model. So if you want to measure RLC, we usually use RLC meters. But in transmission line, in addition to this RLC, we have impedance, characteristic impedance. That's what we're gonna talk a lot. Also, we have to design the wavelength or propagation velocity of transmission line. Usually it is depending on the dielectric material properties. So in transmission line theory, in addition to RLC, we're gonna have to define the characteristic impedance and wavelength or propagation velocity of electromagnetic waves along the transmission line. In addition to that, the line length of line is very important property. I would say most important property of design element in the interconnection at high frequency digital signal is characteristic impedance and the line length. So that is the different requirement of the design compared to the circuit theory. Also, if you want to measure, for example, if you want to measure the line impedance and the propagation velocities, we usually have to use the network analyzer or TDR meters. And using the network analyzer, we are sending a high-speed frequency signals, and we measure reflection or transmission. By measuring the reflection and transmission, we are able to measure the characteristic impedance and the propagation velocities. Using the RLC meter, we will be never able to measure the transmission line impedance and propagation velocities. So this area of transmission line theories are usually the area of microwave theory and microwave engineers. But if you want to design high-speed digital circuits, you should be able to understand and apply the theories, transmission line theories. I think in this class, I would like to expose yourself to those areas so that you will be able to design transmission lines and apply the transmission line theory when you are designing your high-speed digital circuits. So in the transmission line, I would like to say this. What is the impedance of characteristic impedance? I mentioned many times, even though characteristic impedance is the simple meaning, but not many digital designers understand that. So I'd like to remind you the meaning of characteristic impedance. It is transmission relationship which relates the amplitude of voltage wave traveling along a transmission line. It is a relationship here again, amplitude of voltage propagating along the transmission line to the amplitude of current wave traveling along a transmission line. So let's assume that you have a voltage wave. As I mentioned, that in the cross-sectional dimension is very, very small, we can define the voltage across the two lines. And this voltage will propagate along the transmission line that is represented by omega t minus beta g. And then we're gonna also, current will propagate with a same phase I dot sine omega t minus beta g plus pi. This means that in the ideal transmission line, we're gonna have both voltage wave and current wave, and it will propagate at the same phase velocity. That means voltage and current will be at the same phase. In the circuit theory, if you, depending on whether your device is resistor or capacitor or inductor, voltage and current phase will be different. That is the basics of circuit theory. But however, in the transmission line theory, in the transmission line, voltage and current will have same phase. Both are traveling with the same speed and same speed. Then this wave, this is not just standing voltage and current, it's traveling wave. That is why I'd like to say, in the high-speed transmission line, voltage or current is not just staying there. In the circuit theory, they are staying there and it changes only as a function of frequencies. But in the transmission line, voltage and current are traveling at the speed of light along the transmission line, and they have same phase. Now, if we accept that the amplitude and voltage ratio is actually characteristic impedance, it is not a property of device, it is a property of transmission line. And once again, this in the ideal transmission line, and this voltage and current will have same phase by assuming lossless media and homogeneous media. And this characteristic impedance is frequency independence. And this characteristic impedance will control the excitations and deflections of signal along the transmission line. I would say when we are defining transmission line, the most important parameter, design parameter, is characteristic impedance. And characteristic impedance is the ratio of voltage wave to the current wave. Let me continue the basic concept of transmission line. Now, let's think about these coaxial structures. Usually this is suitable for the connection between the computers and computers. Between the device and device, GPU to memory, we usually use the PCB line structures, or on-chip lines interconnection, we usually use the microSIM line structures. But between the system to system, still because of the flexibility of mobility and movement, we to keep the freedom of connections, we still use the many times we are using these coaxial structures. If the cross-sectional dimension L1, if that is very, very small compared to wavelength, we're gonna have a transmission line. Now, in those cases, actually electric field and magnetic field at this cross-sectional structure will have transverse electromagnetic wave. In actual design of interconnections, we are not going to talk many times about this electromagnetic field. Usually we just use the transmission line, but I would like to remind you that if we are sending high-speed digital signals along this transmission lines, we're gonna actually send transverse electromagnetic wave. Then we have electric field. Actually, this electric field will be generated between the two metals. At the cross-sectional, for example, in this case, in electric field will be directed from center material to the outside material. So it's gonna be that direction, also this direction, also these directions. At the same time, we're gonna have H field. H field is usually tangential to the metal surface. And then this electric field and magnetic fields are perpendicular each other. So in this coaxial case, magnetic field will have circular shape. That means at each cross-section of magnetic field and electric field, both will be perpendicular. Because my class is not electromagnetic class, I'm not going to prove it using theoretical derivation from the Maxwell equations. But please remind you that in most of the transmission line case and the ideal transmission line case, electric field and magnetic field are perpendicular each other, and propagation direction is also perpendicular. This electric field and magnetic field and propagation directions are three-dimensionally perpendicular each other. That is called transverse electromagnetic field wave. Why this happens? Because theoretically, I would say our cross-section of dimension of transmission line is much, much smaller than wavelength. We are able to define voltage and current. Then under the condition of transmission, ideal transmission line, we're gonna have transverse electromagnetic wave. Another useful requirement of transmission line analysis is that length of this interconnection should be long. For example, if the length of this interconnection is very small compared to the wavelength, then circuit theory is good enough. But if the length of interconnection is comparable to the wavelength, let's assume that you are designing 10 gigahertz interconnection or 10 gigabps interconnection, then if this length is the millimeter range, I would suggest to apply the transmission line analysis. However, if the length of interconnection is the micrometer range, you don't need to spend to apply the transmission line theory. In the time domain, if the rising time is very short, then you have to apply. That means if the rising time of digital signal is very short, means that you have very high frequency component and wavelength is very short. So even the moderate length transmission line, you have to apply the transmission line theory. So if the clock frequency is becoming higher and higher, then rising time of your signal is very small, then you have to apply this transmission line theory. This is another explanation of transmission line theory. Now we have basic circuit theory and we have field theory, electromagnetic field theory. Usually field theory is applicable to the microwave circuit analysis and antenna analysis. Basic circuit theory is very useful for low frequency circuit analysis. But between the two, we have transmission line theory. Transmission line is actually one-dimensional wave theory. That means electromagnetic wave is propagating only into the G direction. We are not assuming that electric field, this high-speed signal is transmitting into the X direction or Y direction. We are only assuming that this high-speed signal is propagating along the G directions. And we assume that E field and H field is defined between the two matters. Because of that, I would say it is a one-dimensional wave theory, and because of that, we are able to apply the scholastic voltage and current and propagating along the transmission line. So because of this one-dimensional wave, we are still be able to apply voltage and current definition, and we are adding the characteristic impedance and propagation velocities. So I would say transmission line theory is the extension of circuit theory along a line. In other case, I would say it is a specialization of Maxwell equations. Because of this nature of transmission line theory, sometimes we are making connection to the basic circuit theory. Sometimes we are designing I/O circuit coupled with the transmission line circuit such as equalizer design, we should be able to talk both about the circuit theory as well as the transmission line theories. However, when we are talking about EMI, EMC problem, we should be able to talk about antenna theories. So sometimes we are combining this transmission line theory and field theory together to explain the EMI effect. So that is a little bit difficult part. Also, we have to be able to communicate with microwave circuit designers, because sometimes we have to measure the characteristic impedance and propagation velocities. Then we have to be able to use the network analyzers. And sometimes we are obtaining those frequency dependent transmission line properties using the S parameters. So the difficult part of this theory is that we should be able to understand basic circuit theory, field theory, and microwave circuit theories. That is why we are not able to talk about these issues at the undergraduate classes. Then I would like to say why this impedance is important, because it will determine the reflections. That is not we are not seeing any reflections at circuit theory, but in transmission line theory, if the impedance is not well matched, we will see the reflections. So we have to understand the reflections, and reflections will be depending on the impedance. And when we are designing three-dimensional circuits, we will have many stop via line, dielectric, different materials, and then we're gonna see that we're gonna solve for reflections. In order to understand reflections, we have to control the impedance, and also power consumption of your interconnection is also heavily depending on the line impedance, and also depending on the impedance of your line, you're gonna have different simultaneous power switching noise and crosstalk and EMI. All these things are very depending on the characteristic impedance. That's why I'm repeatedly emphasizing the importance of transmission line impedance. Let's talk a little bit more about the impedance. As I mentioned before, the characteristic impedance is the defining the voltage and current wave. So actually, it is the ratio of voltage and current at the traveling wave, and it is a frequency independent properties. But however, in the circuit theory, it is just definition of voltage and current. Usually we define it as a frequency dependency, and because the phase of phi 1 and phi 2 is the depending on the circuit type. So it is very depending on the frequency and the property of your devices. So once again, in the circuit definitions, impedance is the ratio of voltage to current, and it is frequency dependent. But however, in the interconnection is the definition of voltage wave ratio of voltage wave and current wave, and it is frequency independent. This is very simple case where is the we are assuming we have two parallel metals, upper metal and bottom metal. We usually call the top metal as a signal line, and the bottom metal is being called as the ground line. And we have dielectric material who has the dielectric property of magnetic permeability and dielectric constant. And we are assuming the dielectric thickness is much smaller than the wavelength. Then we can calculate, I'm not going to spend time to derive these equations, but at this moment, I would like to talk about the impedance of characteristic impedance of this transmission line. Here we have some numbers, 377. That is the wave impedance. Actually, it is the ratio between electric field to magnetic field in the free space. Because of that, it's purely the material properties, magnetic permeabilities divided by dielectric permittivities. Usually it is 377 ohm, the dimension of that is the impedance. And now we have second properties, material property, dielectric materials. So if you have higher dielectric constant materials, you're gonna have smaller impedance. If you have smaller dielectric materials such as air, you're gonna have very high impedance. So depending on which material we are gonna use, you're gonna have a different impedance. But in the case of on-chip interconnection, if we assume that you are designing your interconnection using the silicon dioxide, then you have to put the number of dielectric constant of silicon dioxide or silicon. In the case of PCB, you're gonna have different dielectric material. So if you, depending on dielectric material, you're gonna have different characteristic impedance. Another important thing is that you're gonna have ratio between the two dimensions. In this case, D divided by W. If you have small D, then you're gonna have small impedance. If you have large W, you're gonna have a small impedance. So if you have given dielectric material epsilon R, you will meet 50 ohm line impedance by controlling D divided by W. So sometimes if because of your processing, if W is already determined, only things that you can control is the D. So D is actually designing element. So usually with the given epsilon R and W, by controlling D, you can make 50 ohm impedance. So if we, because of 377, you have to make a small D compared to W to make 50 ohm impedance. So you have to use very thin dielectric materials to make 50 ohm impedance matchings. So another meaning of this equation is that it is not depending on size itself. It is more depending on the ratio of dimensions. For example, let's assume that you have 1 micrometer D and 1 micrometer W. It will have certain impedance. If you assume that you have 1 millimeter D and 1 millimeter W, still we're gonna have same impedance. So it is more depending on ratio. So you can make a large size cross-sectional the structures, you can still make 50 ohm. If you make a very small dimension, still you can make a 50 ohm impedance. So even though I'm showing you this parallel plate waveguide case, and I'm showing you this equation, but still we can make 50 ohm interconnections using the coaxial structures. It is not depending on structures. By having micro streamline, or coaxial case, you can still make the same impedance. When electromagnetic wave is traveling, they do not care dimensions, or they do not care which transmission line structures. They only care about this number, whether they have 50 ohm. So these are very important things I can explain using this equation. There are some parameters such as in this calculation, such as speed of light in the free space 10 to 8 meter per second. In nanosecond, it travels 30 centimeters. In picosecond, it travels 300 micron. even though speed of light is very, very fast in our human nature, but in distal, high-speed distal domain, where we have to control the timing of signals in picosecond range, the propagation is only 300 micrometers. Usually the thickness of our hair is about 50 micrometers. 300 micrometers is 6 times thicker of our hair. Especially our chip size in these days is centimeter range, or sometimes it could be 12-inch wafers. Then this 300 micron should be very short distance, but it takes picosecond. Then 300 micron should be considered as a transmission line. Also, properties of this wave propagation and impedance and all those things are depending on the materials. And there are two important material parameters of insulator. First one is the magnetic permeability, and second thing is the magnetic permittivity, electric permittivities, and magnetic permeabilities. And once again, I would like to remind you that if you want to change the impedance, characteristic impedance, we have to use different width or different dielectric height. And depending on different dielectric materials, impedance will be different. Also, depending on different transmission line structures, impedance will be different. And also, we have to control the continuity of impedance to avoid deflections. If you have certain connections of transmission lines from receiver to transmitter, and then there will be some discontinuities, and you have to control the impedance to avoid the reflections. There are many different types of dielectric materials, such as silicon carbide and silicon alumina, beryllium, FR4. FR4 is usually used for PCB, and polyimide, and silicon dioxide, usually for on-chip interconnections, and silicon nitride. Sometimes we just use the silicon wafers or gallium arsenide wafers or germanium wafers to make a transmission line. So depending on these materials, we're gonna have different propagation speed and different line impedance. Also, when we are choosing different materials, we have to think about the loss properties, because we have to design interconnection over 10 gigahertz. Some of this material has higher loss than the other materials. So we have to think about what is their loss. Usually loss of this material is represented by loss tangent of materials. Some of the material has a higher cost, and some of the material has low cost. So low cost of your system has to be considered. And in this day, some semiconductor chips are consuming large amount of powers. So to bring the temperature below certain temperature, we have to consider like thermal properties of materials. Sometimes they have some mechanical properties, so we have to think about mechanical properties. By think about these properties, we have to choose this different dielectric materials. Depending on different dielectric materials, we're gonna have different impedance and propagation speed. And the propagation speed is speed of light divided by square root of different dielectric material. So if you have higher dielectric material like germanium, your electromagnetic transmission line voltage and current will propagate very slowly. If you want to design really high speed circuit, you have to use very low dielectric materials, and then you're gonna have very high speed propagations. So depending on material propagation will be different. However, your interconnection will have certain capacitance inductance per unit length. Sometimes your interconnection is very small. You can use these equations to calculate inductance and capacitance. You can apply this to derive the short circuit models. But if you want to calculate the impedance, theoretically, I'm not going to derive this equation. Your characteristic impedance is the square root L divided by C. And if you can apply these equations, and by using the simple Maxwell equations with boundary conditions, we can derive these equations. In microwave circuit theory, you can find all these equations. I would like to give you some my measurement result to make sure that this is all right. A long time ago, maybe 20 years ago, I did measurement. I sent digital signal, 500 millivolt signal, along a transmission line. Transmission line has coaxial cable and PCB line. At the end of PCB line, we have open circuit. Later on, we're gonna talk about the reflections at the open circuit termination. Then we're gonna have 100% electromagnetic will be reflected. That cannot be seen in circuit theory, even though I'm sending 500 millivolt signal, 100% of the signal is reflected here. So totally reflected voltage will be a 1 millivolt signal. So I know the length of interconnection is 1.8 centimeter, and it took 300 picosecond I measured these reflections. And because of this is the round trip from receiver, transmitter to receiver, because it has go to the receiver and it has to reflect it. And then I can see these reflections. And because of this, actually transmitting time from transmitter to receiver along the PCB is 150 picosecond. By knowing this length and time, I can calculate the propagation speed along the PCB, and that is dividing this 1.7 centimeter dividing by 150 picosecond. Then we found that propagation velocity of this wave is now 120 micrometer per picosecond. By having this phase velocities, I can calculate dielectric materials, and dielectric material constant is now, we was able to find 2.77. Why I put the dielectric constant effective? Because some of this is micro streamline, so some of the field is propagating along the insulator, but some of them is propagating along the air. Air dielectric permittivity is 1, and the dielectric permittivity of this insulator is about 4. So we have sometimes between effective dielectric permittivity 2.77. What I would like to say at this moment using this measurement is that even though we are driving this transmission line theory from the Maxwell equations, I verify using the high-speed digital measurement using the oscilloscope and pulse pattern generators. And here, rising time of this signal is very fast, so we are able to apply the transmission line theory. And later on on Wednesday, I'm going to talk about excitations and deflections. But at this moment, let's assume that the transmission line is 50 ohm and our pulse pattern generator is the source impedance is 50 ohm. Because of 50 ohm, of 50% of digital signal is actually generated, and that was 500 millivolt. And because of our transmission line is 50 ohm and the open and the termination is the reflection coefficient is 1, so another 50%, 500 millivolt is reflected. And after round trip of this electromagnetic wave, we was able to measure 1 volt. That is the transmission line theory. And I will give you the transmission line theory more on Wednesday class. And I'm showing you that I was able to measure that. And second thing is that there was time delay in the circuit theory. We are not considering that, but in transmission line, I was able to see the time delay of 100 picosecond. And using very high-speed oscilloscope, we was able to measure this 100 picosecond time delay. And by knowing this length of interconnection and the time delay, we was able to measure the propagation speed, and we was able to measure the line impedance, the dielectric constant of this transmission line. Also, even though I'm not spending time to do that, but by measuring this 500 millivolt, we know that this transmission line impedance is 50 ohm, because 500 millivolt and 500 millivolt then means that your transmission line is 50 ohm. I'm going to derive those equations on Wednesday class. And also, I was able to do the another case with long cables, serial ATA cable, and this time delay, propagation delay was measured 2.15 nanosecond, and cable length was 30 centimeters. And in this case, I was able to show that electromagnetic wave is propagating of 140 micrometer per picosecond. And from that, I was able to calculate the dielectric permittivity of material, that is 4.59. And by showing these two different measurements, I would like to demonstrate the basic properties of transmission line theory. Now, we may have in actual multi-layer structures at PCB, and we have two different cases of transmission line. One type of transmission line is microstream line, where we have ground plane underneath and signal line is on the top. So we have a single ground plane, but we have many transmission lines. So signal line, this is transmission line structures 1, transmission line structure 2, transmission line structure 3. Signal lines are separated, but ground lines are shared. That is the causing crosstalk. And that probably at the last week of March class, I'm going to spend a lot of time to talk about crosstalk effect. And we have two different types of crosstalk, electric field crosstalk and magnetic field crosstalk. And here I would say that in the PCB or circuit level multi-layer interconnection design, we have separate signal line 1, 2, 3, but they are sharing the same ground plane. Of course, sometimes we can separate the ground plane to separate the crosstalk effect between the transmission lines. But 99% case, for the simplicity of interconnection design, we are using the solid plane ground line. And then this line 1, 2, 3 are sharing the same return current path. That means if you have certain impedance at the ground plane, you will suffer a crosstalk between the two separate transmission lines. But the problem is that if we have enough space, we may have only single transmission line. But for example, in HBM, interposer between GPU and memory, we have 1024 lines. They are separated by, this separation is like a micrometer range. So they are very closely spaced. And they are sharing the same return current path. So that's why crosstalk is a significant issue at interconnection design. Sometimes, let's assume that we have to make a connection of more than 1,000 lines between the transmitter and receivers. But if you make so many lines very close, then you have many crosstalk effects. So sometimes some of the interconnection has to go through underline interconnection. And in this case, we have one signal line, but we have top metals and ground metals. So you have two return ground paths. So actually it is 3 metal systems that we call it as a strip line structures. The difficulty of this streamline structure is that it has, if the initial interconnection is on the top, it has to go through the via. MPI has many parasitic, and sometimes it causes resonances. And if you're not carefully designing, it has many high impedance properties or low impedance properties. And that is creating impedance discontinuities. And another problem is that sometimes this is the power plane. Sometimes this is ground plane. So we assume that return current is coming back to the source through the ground plane, but actually sometimes it's going through the power plane. So from the transition from ground plane to power plane will cause a lot of problem, because power plane and ground plane is connected using the battery or decoupling capacitors. And battery and decoupling capacitors has certain impedances, inductance and capacitance. So anyway, at this moment, I would like to say in multi-layer structures, we have usually have micro streamline structures and streamline structures. Microline structures usually have two metal systems, and the streamline structure has the streamline structures. Because of proximity between the two lines, we're going to have large crosstalk problems. And also because of the same return current path, or sometimes discontinuities of return current path, we're going to have severe impedance mismatchings. And we will cover it over the next couple of weeks. I'm going to spend a little bit of time at this moment and then close my, I have to spend 10 more minutes. Yeah. Let's take a look at more closely this transmission line structure, especially to parallel plate waveguide. When we are sending electromagnetic wave along the G direction, voltage and current will propagate along the G directions. But in those cases, when your digital signal is propagating on the top metal, because of the voltage, we're gonna have charge will be induced on the top metal, and the minus charge will be induced on the bottom metal, and electric field will be generated between the two metals. And that is perpendicular to the surface of the metal, and that electric field is perpendicular to the propagation direction G. So when your digital signal will have transition from 0 to 1, instantaneously, you're gonna generate positive charge on the top metal and negative charge will be induced. And this charge, this induction will propagate at the speed of light. Actually, this charge will not be induced at the speed of light. This charge will not travel at the speed of light, but induction of this charge will be traveling along the line. Tangentially, or at the surface of this metal, magnetic field will be induced. If you have magnetic field, then you will induce a current on the top metal, and opposite current will be induced on the bottom metal. And then you will be able to calculate a voltage by integrating this electric field from the top metal to the bottom metal. Also, by integrating this magnetic field from left to the right, you can calculate current from the Ampere's law. You can calculate voltage using the Coulomb's law, and so on. So equal amount of charge will be induced at the bottom metal, and equal but opposite current will be induced on the bottom metal. And this you can calculate the total current by integrating the surface current from 0 to W, then you can calculate current. The ratio between voltage and current will be the impedance. And this whole electromagnetic phenomena and physics will propagate along the transmission line with the speed of light. And when you are talking about the transmission line, you should be able to visualize this. This instantaneous physics, instantaneous electromagnetic phenomena that will actually occur when when you have distal transition from 0 to high. At this moment, at this steady state, this electromagnetic field doesn't stay there. You don't need to worry about that. We do not have this electromagnetic wave at this steady state, distal state. Only this transition state at very fast rising time, it has very large amount of high frequency component. Then you have this phenomena. At this instantaneous moment of distal transition from 0 to high or high to low, at this instantaneous moment, when this transition is traveling at this position at your transmission line, instantaneously you're gonna induce the current in this G direction and minus G direction at the bottom metal, positive charge on the top metal and negative charge on the bottom metal. Then you can define the voltage and current, and magnetic field and electric field will perpendicular each other, and that will propagate along the transmission line. And then this propagation and voltage and current will be depending on the characteristic impedance. That's why we're gonna talk again and again about the characteristic impedance. Now, let me explain it a little bit more. Let's assume that you have a PCB or on-chip circuit is okay, same. You have driver, you have receiver. At low frequency, let's assume that we are connecting driver to receiver. Then you have current at low frequencies, and return current will come back through the ground plane. Where this return current is coming, because it goes through the minimum inductance path or minimum resistance path. But if your frequency is becoming higher and higher, your loop, or I'm sorry, don't close your window. So this return current is going to this path, shorter and shorter path. If you increase the frequency higher and higher, you're gonna your current loop size becoming smaller and smaller, because that is how you can minimize the inductance. If you send a DC signal from driver to receiver, it goes through all those places with the minimal resistance. But if you increase the frequency higher and higher, your return current goes through very short paths. That is because your driver wanna feel minimal impedance so that you can send higher current and higher voltage. In order to do that, naturally, your return current goes through this minimal loop size, just underneath the wire. In the transmission line, you are sending very, very high speed signals, so your return current will go through just underneath of your transmission line. That's why when you are sending your signal, high frequency signal, most of your return current will go through underneath of this metal in this area. Your return current will be mostly on this area. And mid-frequency range, you will send a signal and your return current will come back just underneath of your metal, and that will constitute of your transmission line. This becomes your transmission. I'm sorry. This becomes your oh. Oh, forget about it. So your return currently will be mostly on this area in the transmission line. But more things I would like to say is that if you are sending really high-speed digital signal, you will have instant at the transition from 0 to 1. At this moment, you're gonna have only instantaneous current. G direction and minus G direction will appear only at this area. Only this area. In the rest of the transmission line, it is a DC state. Only high-speed transition occurs, you're gonna have instant positive current at the top metal and return current on bottom metal. This is another way. So once again, return current is under the bottom metal. So today I was trying to explain the basic concepts of transmission line and what is important properties. And next Wednesday, I'm going to extend this transmission line theory to talk about excitation, propagation, and multiple reflections. Next week, I'm going to show real examples of interconnection circuit to control this excitation, propagation, and multiple reflections. Because I'm giving lectures using this Zoom internet, it is very difficult to convey my ideas to you. If I am staying in front of blackboard using the chalk, I can show you my motions of action to explain all this. And I'm really sorry for that, but this is what is going on in this COVID-19 era. So this is end of my class today, and thank you for your attention. 한국말로 좀 하겠습니다. 한 10분만. 여기에 뭘 얘기하고자, 여기에 좀 많은 얘기가 있으니까 여기서 얘기를 하겠습니다. 트랜스미션 라인 시어리라고 하는 거는 하여튼 이 디지털이 빠른 속도로 이렇게 갈 때 이 트랜지션 할 때만 적용되는 겁니다. 이 DC 스테이트에서는 이게 제가 아까도 말했지만은 이 트랜스미션 아이오 인터커넥션을 하려면 서킷 티어리하고 트랜스미션 라인 티어리, 전자파 티어리가 막 섞여지는데 오늘 그런 것 같아요. 여기서 보면 이 트랜지션이 일어나는 이 구간에서만 트랜스미션 라인 현상이 일어납니다. 그리고 이 트랜스미션 현상이 일어날 때 라인 길이에 비해서 이게 굉장히 짧은 순간이면 그 현상을 설명하려면 이제 라인 임피던스나 전파 속도가 우리가 고려를 해야 되는데 전파 속도나 뭐 이런 걸 하기 전에 또 다른 측면은 이 필드 시어리하고 좀 연결을 시킬 필요가 있어요. 그걸 지금 하고 있는 겁니다. 필드 시어리 입장에서는 이 트랜지션 현상이 빛의 속도로 가는 거예요. 전류나 전자가 빛의 속도로 가는 게 아니라 여러분들이 도미노를 쭉 세워놓고 떨어뜨리면은 넘어가는 현상이 어떤 속도로 이렇게 쭈르륵 넘어가요. 그렇지만 그 넘어지는 블록 자체가 빛의 속도로 가는 건 아니에요. 자, 도미노를 봅시다. 도미노가 한 수십 개가 이제 마루에 있으면 뚝 떨어지면 뚝뚝뚝뚝 떨어져요. 1초에 한 개씩 넘어져요. 그럼 한 개당 1초죠. 근데 도미노 자체를 보면 도미노는 움직이는 게 아니에요. 자, 이 넘어지는 현상, 이 트랜지션이 일어날 때만 이런 현상이 일어나는 거예요. 도미노가 넘어지고 난 다음에는 뭐 전압이든 전류든 가만 그냥 DC 스테이트로 있는 거예요. 도미노 자체는 그러니까 넘어지는 순간에는 그 현상은 보면 넘어지는 현상이 넘어갈 때는 트랜지션이 일어날 때는 비속도로 갈 때 그때 전자가 위에 유기가 되고 마이너스 차지가 아래쪽에 유기가 돼요. 똑같이. 전자파는 두 개의 메탈이 있으면 하나가 그라운드냐 하나가 시그널이냐 이런 한국말을 이해를 못해요. 영어를 이해 못해요. 얘네들은 이제 맥스웰 이퀘이션만 이해되는데 그리고 이게 트랜지션 일어나는 그 순간에 전류가 유기되고 아래쪽에 반대편 유기돼요. 그러니까 이 그라운드나 시그널이 끊어지거나 이러면 이 전류가 끊어지니까 그러니까 이 트랜지션 현상에 가지 못하고 되돌아와 버린다는 거죠. 이 트랜지션 현상의 중요한 게 반사와 전파인데 그걸 컨트롤하는 게 임피던스입니다. 그런데 이 중간에 전자가 유기되면서 아래 위로 일렉트릭 필드가 생기고 또 그때 전류가 유기가 돼요. 자기장에 의해서. 근데 이 전기장과 자기장은 직각이고요. 이 전기가 순간적으로 전류가 흐르는데 반대편에는 아래 전류가 흐르는 이 현상이 비스의 복도로 가고, 이때 단면적이 작으니까 이 전류를 전압을 인테그레이션하면 일렉트릭 필드를 인테그레이션하면 전압이 되고, 전류를 인테그레이션하면 전류가 돼요. 그게 이제 스테릭 필드에서의 그 바운더리 컨디션에서 얻을 수 있죠. 그 현상이 비스의 속도로 가니까 전류와 전압이 비스의 속도로 간다. 이게 비속도로 도미노가 끊어지는데 도미노가 중간에 뭐 이상한 게 하나 껴 있다. 빨간색 도미노로 오다가 나무로 만든 도미노가 오다가 플라스틱 도미노로 오면 떨어질 때 속도가 다르고 미는 힘이 다를 거 아니에요. 그러니까 임피던스가 달라지면 이 현상이 이제 여러 가지 현상이 일어나는데 그 다음 주에 수요일 날부터 하겠습니다. 근데 또 서킷 티어리, 이건 이제 제가 필드 티어리와 트랜스미션 라인 티어리를 이렇게 연결 본 건데, 한번 회로 이론과 또 연결시켜 보면, 회로가 이제 드라이버에서 리시브로 전류 보내는 이렇게 돌아오죠. 킬로헬스나 메가헬스 되면 이 루프를 이룹니다. 근데 루프를 이룰 때 어디로 돌아오는지 우리 회로에서는 안 하지만, 우리가 실제로 만들려면 PCB로 만들면 PCB에 이제 그라운드로 돌아오는데, DC에서는 아무데나 다 저항을 최소화하는 방향으로 돌아오는데, 조금 주파수가 높아지면 인덕턴스를 줄이는 방향. 왜냐면 우리가 그라운드는 임피던스가 제로라고 보는데, 그렇게 하려면 이 루프 사이즈를 줄이는 방향으로 오죠. 근데 이제 메가헬스 넘어가면 이 루프 사이즈의 인덕턴스가, 그러니까 전류가 안 가요. 그래서 여러분들이 학부 때 실험실에서 브레드보드로 이렇게 라디오 만들면 안 도는 게 고주파로 그 와이어가 가지 않기 때문에 그러는 거고, 그라운드 리턴 페넌트도 안 만들어줘서 그랬을 수도 있어요. 그래서 이제 한 메가헬스에서 기가헬스로 가면 시그널을 가면 바로 밑으로 돌아옵니다. 이제 트랜스미션 라인이 되는데, 기가헬스가 넘어가면 이 전체로 전류가 가고 오는 게 아니라 인스탄테니어스하게 이 트랜지션이 일어나는 부분만 순간 전류가 유기되고 순간 리턴 커런트가 유기되고 이런 현상이 일어나게 됩니다. 자, 수요일은 이런 현상을 이용해서 실제로 디지털 시그널을 보낼 때 어떤 현상이 일어나는지 타임 도메인 어널리시스를 해보도록 하겠습니다. 내가 이렇게 열심히 강의를 하지만은 좀 쉽고 편안하게 하려고 그랬는데 또 해보니까 이렇게 너무 길어지고 어려운 것 같은데, 여기 정현이 들어와 있죠? 수업에 마이크 클 수 있나요?
네, 교수님 안녕하세요.
지난 시간에 내가 정현이한테 물어봤나요? 종현이한테 물어봤나요?
종현이 형한테 물어보셨습니다.
정현이가 오늘 수업 한번 좀 요약해 줄래요? 제가 뭘 얘기를 했는지.
아, 네, 알겠습니다. 우선 그 트랜스미션 라인 설계를 위해서 임피던스 디자인이 굉장히 중요한데
음,
그 이유가 리플렉션이나 프로퍼게이션 같은 문제가 있고 그
네,
문제랑 관련이 많고 또 전력 소모 등의 여러 문제랑 연관이 있기 때문이라고
맞습니다. 아까
이랬습니다.
그런 슬라이드가 있었습니다.
네.
네,
그리고 또 이러한 트랜스미션 라인의 설계가 그 어렵고 복잡한 이유는 기존의 회로 이론에 더불어서 전자기장에 대한 고려도 필요하고
음,
또 그 마이크로웨이브 네트워크 분석 같은 여러 가지 문제들이 엮여 있기 때문에
그렇습니다.
네, 그래서 학부생 수준으로는 이해하기 어려운 부분이 있었고
음,
여러 가지 고려가 필요하다고 이해했습니다.
네, 좋습니다. 제가 조금 더 애다하면 그 이제 투 메탈 트랜스미션 라인의 경우 돌아오는 커런트 패스가 존재를 하는데, 우리가 그냥 회로 설계할 때는 그라운드는 그냥 빗겸쳐 놓고 마는데, 하이스피드 디지털은 시그널 라인 설계보다 여기서 그림에서 나오는 리턴 커런트 설계 시간을 10배 정도 더 해야 된다. 왜냐하면 전자파 입장에서는 투 메탈이 똑같이 그냥 전류가 유기되고 차지가 유기될 뿐이지, 근데 우리가 PCB나 칩 설계할 때 시그널 라인만 신경 쓰는데 똑같이 그라운드 라인 설계. 그라운드 라인이 이렇게 끊어지면 임피던스가 끊어져서 반사가 일어나고 이런 게 있었고요. 또 하나 이제 임피던스가 중요한데 전파 속도. 전파 속도는 유전 상수가 결정하는 거고 임피던스는 물질 상수하고 디멘전의 크기의 비율이란 말이죠. 그러니까 1mm, 1mm짜리 단면도 55옴을 만들 수 있고 마이크로미터, 마이크로미터. 그러니까 온칩에서는 마이크로미터 단위로 설계되고 PCB는 100마이크론, 케이블은 밀리미터가 돼도 55mm 임피던스의 컨티뉴이티를 유지할 수 있다. 그러니까 구조와 상관이 없고 비율과 상관이 있다. 절대적인 크기가 아니라 그런 물질이고 그러니까 비율을 잘 조정하는 게 임피던스를 맞추는 거다. 그런 말씀을 드리고 우리 회로 이론에서도 많이 안 다뤘는데 하여튼 이게 전류가 우리가 왜 학부 때 라디오 실험하면 잘 안 되냐 이런 전파로 갈 수 있는 길을 안 맞춰줬기 때문이다. 네. 근데 이 전파로 굴러가니까 우리가 뭐 트랜스미션 라인 해석할 때 자세히 볼 필요는 없지만 왜 갑자기 이런 현상이 이해할 때는 어떤 데는 회로로도 이해를 해야 되지만 또 하나는 이렇게 필드 거기가 이래서 전류가 이런 픽처를 가질 필요가 있고요. 이런 픽처 단면 하나에 내가 그린 요 일렉트릭 필드, 마그네틱 필드, 차지 커런트가 그 자체가 빛의 속도로 흘러간다. 네. 근데 또 어려운 게 뭐냐면 우리가 이제 중간고사 이후로는 전력 회로를 설계할 텐데 여기서는 55옴으로 해주면 되는데 전력 소모는 볼테이지 드랍 작게 하려면 미리오음이나 마이크로오음으로 만들어줘야 돼요. 우리가 회로 이론에서는 아예 전력 자체를 고려 안 하지만 전력 전자하는 사람들은 전력 회로의 임피던스도 고려하는데 우리 수업에서는 전력도 빛의 속도로 가는 이 현상을 또 그려야 돼요. 전력 회로를 이렇게 또 일렉트릭 필드, 마그네틱 필드 비슷. 왜냐하면 디지털 회로가 순간 스위칭할 때 빛의 속도로 전력 회로에서 또 전자를 공급해 줘야 되거든. 그리고 파워 회로가 또 어려운 게 빛의 속도로 공급망 회로를 설계를 해줘야 돼요. 그게 저는 한 뭐 이런 분야를 20년 했으니까 알고 보면 별거 아닌데 또 생각해 보면 또 처음 생각하기 어려운 측면이 있는 것 같습니다. 전력을 빛의 속도로 보내준다. 제가 무선 전력 전송도 하고 자동차 전력도 하고 디지털 전력도 하고 우리 학생들 파워 인테그리티를 하는데 그게 전력 전자 하는 랩하고 나하고 차이는 뭐냐면 거기는 킬로헬스 전력을 해요. 스위칭 IGBT나 인버터. 우리는 기가헬스 전력 회로를 하거든요. 기가헬스 하면 이 임피던스 매칭 또 빛의 속도 이거를 전력망에도 또 그대로 적용해야 된다는 거. 그런 점이 있습니다. 자, 오늘 제가 사실은 1시간만 하려고 했는데 1시간 반 하게 됐는데요. 그 칠판 앞에서 하면 모션도 하고 막 그 액션도 하면서 하면 여러분들도 재밌게 할 텐데 줌으로 하는 게 그런 단점이 좀 있다 이런 생각이 들고 그 칠판에서 하면 학생들 나와서 그려보라고도 막 하고 이럴 텐데 그러지 않은 게 좀 아쉽습니다. 근데 장점은 유튜브에 기록이 남으니까 다시 보면 뭐 무슨 뭐 말인가 이런 게 알 수 있겠죠. 여러분 수고하셨습니다. 수요일 날 뵐 텐데요. 수요일은 여기보다 한 발자국 더 들어갈게요. 한 발자국 한 발자국. 네, 재밌게 노력해 보겠습니다. 수고하셨습니다.
네.